In part 2, and I know I already alluded to this, so it kind of gives it away, but what do you think the derivative of x squared plus 3x minus 7 is? 2x for the x squared, plus 3 for the 3x, plus 0 for the minus 7, which you wouldn't have to write. And that is what happens correctly. So when you are adding and subtracting functions, when you want to find the derivative, you can find the derivative of each thing separately. Again, in university, what's going to happen most likely when you learn this is your professor is going to introduce something like this and then use the definition of the derivative to show it. And then use that as a proof to say, now we're allowed to do this. And for the most part, you won't be allowed to do anything unless you've proven it in class to be able to do it. So even your power rule, how do you prove a power rule? And that's where a lot of students in university sometimes get lost because they're like, the professor does this really complicated proof, and then he goes, okay, now you can use this simple rule. And you're like, I don't know what you just did there, but I'll agree with it. At times, yes, at times, no. So the nice thing for us, we're not going to go into all these proofs. This one's actually really easy to prove using the definition of the derivative, but we're not going to go there. Okay? So what does that mean? Let's find the derivative of a couple. Again, these. Imagine, though, to get really, like, you're like, oh, this is easy now. You just go like this. Okay? Yay. Okay? After you do it, think about using your definition, because you could get this one with the definition of the derivative on tomorrow's quiz. How much longer would that take? Quite a bit longer. Okay? How would you use the definition? Well, you would set up your limit as h goes to 0. Okay? You would have 8x. You'd plug in x plus h. Will there be a 3 there? Minus 4. That's your first thing, plugging in the x plus h. Subtract, and then you would rewrite this 8x squared plus 3x minus 4. Expand everything, combine your like terms, factor out your h, and you get this. Okay? Okay, I like these ones with 2 terms because you have to plug the x plus h into x twice. The nice thing now, though, is you can check your answers. You know what the answer should be. Okay?
We can be hurting ourselves when we do that.
Yeah. So it might be painful if you can't. You know what the answer is. You just can't get it. That's true.
Would you get one
but
correct answer, right? Yeah, write a bunch of crap, but the answer.
Okay. Here's a little bit more awkward notation. This is a mapping notation for a function. The function f takes the value x and maps it to this. So it's just another way of saying f of x equals. So our derivative would be, okay, we'd have 18 over 3, which will be 6, x to the negative 1/3 plus 2, x to the negative 4/5.
What's the point of having it written like that if you're going to write your answer? It's just a different.
I'm just showing you different notations that you could run into.
For the next one, we'll just keep the.
So, do you want me to write this? The proper the notation that would match with this would be f prime maps x to that. But so do we have any rules that have things like this? Not yet. What did you want to try?
Take the, because instead of doing the derivative, take the 2 out in front
You want to take the 2 out in front.
So then I did subtract once you handled the outside.
Yeah.
And now you just you handle each individual thing on the inside.
And so what would you, then how do you handle the things on the inside?
2x minus 0. You just
So how do I write that though? Like, should I change this inside? Should I? So I should.
Wow, you don't even have to worry about
So I should just change that to 2. You are very close, but unfortunately I haven't taught that to you yet, and so all we have right now is the rules that we know, and the only thing we can do with this is fiddle with it until it matches the rule that we have. So I'm saying, well, x squared minus 4 squared means this. And if I multiplied that all out, I would get x to the 4 minus 8x squared plus 16. And now it's in a form that we know how to do the derivative of. So you were close in finding a new shortcut for this one, but ultimately you failed. So we have to work with what we have. Right? If you had a test out of 100, this is really close to 100 out of 100. But ultimately, it's still a fail.
It's almost, it just was a decimal point. It's almost 25 out of 30. To simplify further, you just
We can leave it like this, or if you would like to write it factored, often factoring things is a nice way of writing it. What is this factored to? Like that. And can that be factored even further? Yes, it could.
Now this is the purest form right here.
That could be someone that's like a show that.
Now, it factors really nicely. Prove that it equals to that. And factoring it nicely, this, here you could quickly find all of your x-intercepts. That could help you graph it.
I noticed that x squared minus 4 is the same thing we started with. But like, then you multiply by 4.
So now we go back to,
You missed a lot.
now we go back to what Peter had started with. Okay? Look.
Hi, Mr. Taylor.
Hello.
Sorry for interrupting. Could you
All right, so what Ramsey said is he noticed there's an x squared minus 4, and we had an x squared minus 4 to begin with. What Peter said is that at the beginning he said, I want to take that 2 out in front, and that would make that, that would make this, but it doesn't quite match up. What's missing?
You take the
And now Peter wanted to do the derivative of the inside, and the derivative of the inside is 2x, and it all multiplies out, and it does work out to be the same thing. Is that just coincidence?
no.
Maybe, maybe not. We'll see. We'll see it later on. But it is kind of interesting that it worked out to be like that.
Close doesn't mean anything. You were close to you almost
But
landmine is given.
when we do learn that method for this last one, you'll feel like that method is quicker, and you'll want to do it that way. And in this case, it is a little bit quicker. The interesting thing is we're going to learn another method for this one, but in this case, it won't be quicker. So currently, with the multiplication here, this doesn't fit the form that we can do the derivative. But if we multiply this out, okay, first of all, maybe you want to change that cube root of x to x to the 1/3. And now we have to use our exponent laws. What happens when you multiply bases that are the same and the exponents are different? You add the exponents. So what will I get? Whoop, I got 6x to the power of 7 over 3 plus 3x to the power 4 over 3. So you'd have to add 2 plus a third is 7/3. 1 plus a third is 4/3. And now we can apply our exponent laws. So y prime, I think this had before dy dx. Not that it really matters, but dy dx will be 14x to the 4/3 plus 4x to the 1/3.
Okay, 7 times 6 divided by 3 is divisible by 3, sorry.
Right, so when I'm doing the mental math here and I'm thinking about multiplying these two in front, it makes it a lot quicker if I do the 6 divided by 3 first and then multiply by 7, rather than doing 6 times 7 and then dividing by 3. Both give you 14, but mental math-wise, 2 times 7 I think you can do faster than you can do 42 divided by 3.
Definitely. 100%. I have no idea. 6. You don't have to. You can do this.
So use your algebra skills. How do you take this one and rearrange it so it looks like something you could differentiate? And there is a rule later on that allows you to do this, but this might be quicker.
Would it be 3x?
Hmm? Well, the x you could, but not the 3. Careful. Ooh, I like it. Seen a couple of different techniques so far. Of the two techniques I saw when I'm walking around, if I had to pick my favorite technique uses the skill of unadding fractions. You know how to add fractions, right? How do you add fractions? Get a common denominator and then add the numerators. So if you can do that, can you unadd fractions? Of course you can. So unadding fractions, what does that mean in this case? Well, before they were added together, can you imagine them looking like this? And then if I simplified each of those, this one will be 2/3 x to the 6, and this one will be 3 over x, or 3x to the minus 1. And now it's in a form that you can find the derivative, bring the 6 out in front, bring the negative 1 out in front, and we have our derivative. I guess these ones said find dy dx. Six, yes, 4x to the 5, thank you. Sometimes when you make big mistakes, you want to